Hi everyone, my name is Ing Sarah, and today I'm going to talk about optimization calculation in computational chemistry. Let's get started. Well, first off, let's take a look at a few softwares that are used to conduct quantum calculations, used to run quantum calculations. There's Gaussian, which is also used in the Freedom Lab at Lehigh University. It usually comes with Gauss View software that allow you to build the molecule structures and create some sort of settings for a certain specific calculation, and then create the input file to run in Gaussian. There are also a few more softwares that are used, such as Orga and NWChem, etc. All right, now let's talk about our main subject of the day, which is optimization calculation using DFT or density functional theory. Um, just for a quick refresh on DFT, it is one of the methods to solve the Schrödinger equation. But instead of taking an exhausting approach to solve the energy of each individual electron, it looks at the overall density of the electrons, which makes it more fundamental quantity compared to just solving a wave function, leading to less energy intensive in computing, which is a good thing. So optimization calculation is usually done at the very first step when you study a molecule. There's a few reasons for that. So first, you want to look for the most stable structure in nature, the predicted most stable structure in nature. And then this gives the lowest energy configuration that you will use to predict different kinds of properties leading out of the very first configuration you got as an output from the optimization calculation. This can be non-existing chemicals or existing chemical, which is one of the most advantageous perks in computational chemistry. It's really cool. All right, let's take a look at one example which related to my research study that I did in my undergrad. So acid violet 3 structure, it was predicted to have this structure on the left or the IUPAC structure. You would think that maybe this is the lowest energy configuration, which is similar to the structure on the right. We call that transenal, similar to the IUPAC structure. We would think that is the lowest energy configuration. However, it in fact isn't in this case. After we got the energy from the optimization calculation, it says that in fact transketo is the one with the lowest energy, or transketo is the lowest energy configuration. And with that, we can use the very configuration to study different sort of properties in a more accurate approach based on the results of optimization calculation, thanks to that. All right, and here are the example of the outputs or the results of optimization calculation. So the first step, that is a guess structure. That is the very first structure that you built, that I built. It has the highest energy, and then it slowly iterates by adjusting the location of each atom slowly, and the energy going down and down and down until on the step 18, it hit the lowest and remained constant until the last step, meaning that is when the structure is converged, and that is the lowest energy configuration. And from there, we can use it to study and obtain different kinds of properties, such as the transition states, multiple kinds, to study the isomerization in the ground states of acid violet 3, or the predicted UV spectra that comes into handy to compare it with the experimental results, or just sort of navigate the efficiency of the methods you use for computational chemistry. All right, thank you so much for today, and I hope you having fun learning a little bit about computational chemistry. Thanks so much. Bye.